Something is happening. Good. So I think we are online now. How do I get back to Zoom? Okay. Good. So we were talking about duality, and this is one of the important, one should say, theoretical results, but it has consequences to practical applications of linear programming as well. So we were discussing linear programs in the equational form. So let us continue with that for some time, and then we will discuss about linear programs as they more often occur. Yeah. So it looks like this. So we try to maximize some objective function subject to a set of equalities and non-negativity constraints. Okay. So now, suppose we have these equalities, and by taking linear combinations of them, see, this is a bunch of equations. The variables appear on the left and the constants appear on the right. So we can take linear combinations of these equations and you will get other equations. Now, each of those other equations must necessarily hold for every feasible solution. Okay. So suppose we start with this system and multiply the equations with this constant. That is, the first equation we multiply by y1, the second by y2, the third by ym. We are completely free to choose our yi's. So if we use these as our scalars for obtaining the new equation, then the final equation that we get looks like this. Okay. So x here is still a variable, but these yi's are, let us say, constants, m of them, because there are m equations here. And similarly, we get only one scalar here. Now, suppose it so happens that we are able to find a y. We are able to find a y so that this quantity starts looking like our original objective function. Now, it may be possible, may not be possible. But suppose there is such a y, then that basically forces the optimum of this LP. For example, suppose we are able to find a y so that y transpose A is C transpose, then let us multiply both sides of this equation by x. And what do we get? Y transpose AX. Yeah. So C transpose X for every feasible solution X. Yeah. Or actually, as far as the first equality is concerned, this is true for every X. So for every X, C transpose X is equal to Y transpose AX for every X. Now, if X also happens to be feasible, that is, if AX is equal to B, then this AX we can replace by B. And what have we obtained? We have obtained that no matter what your feasible X is, the value of the objective function will be equal to C transpose B. Basically, if this C transpose is a linear combination of the left-hand sides of these equations, then the value of the objective function, or the objective function is equal to certain optimum, is actually a consequence of these equations. And this consequence is derived by just multiplying equations by some scalars and adding them up. And there's nothing very great that is happening. You're probably like quite aware of all this from your linear algebra course. Okay. So if you find such a y, then Y transpose B will already be the optimum solution.
It might be the case that LP is not feasible, right?
Yes. So if it is feasible and we are able to find such an X,
Such
then,
and Y.
sorry, yeah. If we are able to
Okay.
find X and Y, so that then for every feasible solution, this is true. Yeah.
Yes, yes.
Yeah. If, yeah, sorry, yeah, I should say that if it is feasible, then this will be true. Yeah. Now, here we did not make use of the fact that X is greater than or equal to 0. Okay. Yeah. I mean, the optimum was forced on us by the equation. Okay. But if X is greater than or equal to 0, then it turns out that, you see here I said, suppose we choose Y so that this. I mean, we may not be able to find such a Y. But here we are insisting that this Y be such that Y transpose A is exactly equal to C transpose. Okay. But if we know that this X has some additional constraints, for example, the non-negativity constraints, then we don't need to impose such a strict condition. What can we get by? We can get by with this. Yeah, so let us do. So suppose we can find a Y, this time such that Y transpose A is greater than or equal to C transpose. Not equal to C transpose, Y transpose A is greater than or equal to C transpose. Then we can play the same trick. Yeah. When we multiply both sides by X, this inequality continues to hold because X is non-negative. Okay. Because X is non-negative, we can, if you multiply, yeah, what should I say? This inequality holds component wise. The first component of C is less than or equal to the first component of this vector. Yeah. So the first component of C transpose, which is a row vector, is bounded by the first component of this.
You also need the coefficients, the coordinates of Y to be greater than or equal to 0, right?
Sorry, the coordinates of?
The coordinates of Y should be greater than or equal to 0.
No, we are continuing to be in the equational form. Okay, the constraints are still equalities.
Okay.
Okay, so constraints are still equality. So this, sorry, where did I go? Okay, sorry. Yeah. So the constraints are still equality. So yeah, there is no constraint on Y. We just find any real Y such that this is true. Okay, if any Y this is true, then I mean the meaning of this inequality is that component wise, for each component, whatever appears on the left is dominated by what appears on the right. Okay. Then if I multiply that by an X, yeah, any X at all, which has all components greater than or equal to 0, then the contribution that I get from the left and the contribution that I get from the right will also satisfy this inequality for each component. So when I add them up, this inequality will continue to hold. Is it clear? If this holds, then multiplying it by an X which is non-negative will ensure that this is true. But right now, we have this. AX is equal to B because we are still working in the equational form. So this quantity is equal to this, and we have a theorem similar to what we had before. That is, last time we knew that if there is a feasible X, then that feasible X will already be optimum, and its value is completely determined by this magic Y, which was designed for this. But now we can only say that this Y transpose B. Yeah. So we are taking these equations, we are adding them up, but ensuring that the left-hand side dominates the objective function. Then whatever we get on the right-hand side will form an upper bound for the objective function. Okay. So that is the message of this equation. And what should we do? Suppose we've been given a linear program and we are wondering, it's a maximization program, and we are wondering how small can we make this upper bound? That is, what is the lowest value that follows from these inequalities? Well, the lowest value, yeah, I mean, that follows from this inequality is in fact the optimum. Okay, it follows. Yeah? That is, anything which is feasible cannot take a value more than optimum. Yeah. So the fact that the objective function is less than the optimum is a consequence of these inequalities. But we are now trying to derive consequences by a certain algebraic method. That is, by taking these equations and multiplying them by scalars and trying to ensure that a certain relationship holds between the left-hand side and the coefficients in the objective function. Using that method, what is the best upper bound that we can obtain? Well, we should try to design our y so that this inequality holds, which is written here by just taking the transpose. Yeah. A transpose y must be greater than or equal to C. And we would like to minimize the right-hand side. Yeah, we would like to minimize, if we multiply those equations by this y, what accumulates on the right-hand side is this. And we would like to minimize this, and y can be any real number. There is no non-negativity. And the kind of pleasant thing about this is that this also starts looking like an LP. Yeah. So we started with the mission of trying to find an upper bound for the optimum of the original linear program by using a certain method, by just trying to combine equations by multiplying them by some scalars. And the best thing we can hope for, the best upper bound that we can achieve, is expressed by this linear program. Okay. So now, from this linear program is called the dual of the original linear program. The original program is sometimes called primal, and this is called dual. Okay. Now, yeah, so let us just work with this special case. So I'm saying special case because we are working with equational linear program. Of course, every linear program can be converted to equational linear program. But later on, we will state the duality theorem or the duality idea for general linear programs. Okay. Yeah. But I would like to continue with this for some time and then go to that. So what do we know from this? That if X is a feasible of the primal and Y is feasible for the dual, okay, then the objective function for the primal is given by this. Okay. Yeah. Sorry, what am I writing? I made a mistake already. Sorry, what am I doing? Yeah, so what I've written is completely wrong, but no, sorry. So ignore the parts here and here for the moment. Okay. Yeah. So what we know is that for every feasible X for the primal and for every feasible Y for the dual, we have that this quantity is less than or equal to this quantity. Okay? Because of our discussion before. The moment we find a feasible solution for the dual, it imposes a restriction on every feasible solution. We find one feasible solution for the dual, it imposes a restriction on every feasible solution for the dual, for the primal. That means the objective function for every feasible value for the primal is bounded by the objective function realized for every dual feasible solution. And now, in particular, for the best objective function, yeah. So I shouldn't have written this. What is written is not quite right. So maybe I should erase these things. Yeah. So So this part is true always. And then if you put a max here and put a min here, you will get the objective function at some value x star, and the objective value some. I'm messing this up very badly, but I hope you understand. Please ask. I didn't say this very well, but yeah, is there a question? Yeah. So if you maximize the left-hand side, you get this. And if you minimize the right-hand side, you get this, because that is the definition of the dual program. And since this is true for every individual feasible solutions, it must be, this inequality must hold for the between the optimums on the two sides. Oh, I'm sorry, I did not, what I wrote was completely all right. I just said objective of the primal, and I somehow got confused and thought I had written optimum for the primal. Okay, if I'm just saying that objective, yeah, let me put it back. This is indeed the objective of the primal at x, and this is indeed the objective of the primal at y, and the objective of at x and y satisfy this property. But notice that this was a maximization problem and this was a minimization problem. Yeah. Sorry, yeah. Kavita, you want to say something better?
No, nothing, Jayakumar, is perfect.
It's fine. Okay. Yeah. Yeah. So far, this is where we are. Okay. So the questions, some of them you already asked. So suppose, is the dual feasible? Yeah. I mean, and is the dual unbounded? So what we know is that if both are bounded, then both of them will have optimum solutions, because this is something we discussed already. That is, whenever linear programs are bounded, they have an optimum solution. Okay. And then we will be able to make this statement. That is, the optimum of the primal is the optimum of the dual, which is what I was struggling with earlier. Yeah, I should have said it now. If both are bounded, so their optimums exist, then this is the relationship. Yeah, even though this is a maximization problem, the max version is less than the min. Okay. Yeah, it seems to go the wrong way, but that is what it is. Now we can ask, when does this equality hold? Suppose both of them are bounded. When does this equality hold? And the amazing theorem is that this equality always holds. Okay, so for every linear program with a bounded optimum, yeah, suppose both of them have bounded, or rather, if an optimum of the primal exists, then the optimum of the dual will exist, because yeah, if the optimum exists, in particular, the primal is feasible. If it is feasible, then the solution at that feasible point forms a lower bound for the dual program. That means the dual is bounded. And the moment dual is bounded, it must have an optimum solution. So if one of them has a optimum, automatically the other one's optimum, must exist. And this theorem, the strong duality theorem, so this, that there is always equality in this case, is called the strong duality theorem. The fact that this inequality holds is called the weak duality theorem. There is more that can be extracted out of this statement. We will discuss that now. Okay. So let me first quickly tell you why strong duality holds. Okay, it actually follows from simplex, and I want to spend about 5 minutes to try and see if you just see it out of the simplex tableau. Okay, so I would really like you to ask questions. Okay, so we were trying to, so let's go back to simplex. We were trying to solve such an LP. Okay, we are trying to maximize something subject to an equality and this. And then for this, we will build a dual LP. And what are we trying to say? We would like to find a y here which satisfies this inequality. Yes, so it should be feasible for the dual LP. And that y should yield the same value as the primal LP. Okay. Yeah. So let's assume that we arrived by the simplex method at a solution for this LP. So what would happen? We would initially write the LP in this form as a tableau. Yeah, so we would write this tableau, and this was the initial basic feasible solution. And these were the variables that were initially set to 0. And you remember I once played around with these sub-matrices of the original constraint matrix. And we were able to write the objective function also in terms of some value. Once you eliminate xb from the expression for C transpose X, some scalars started appearing because we use these equations to eliminate them. So some scalars started appearing, and what remained, unfortunately I made a mistake, should be just, so what remains in the bottom row of the tableau is only the variables corresponding to the non-basic variables. And then suppose this LP had an optimum. Okay. So what would happen? We would run simplex and we would arrive at something like this. That means our basis would change perhaps. So this is BF, okay, but it's very cluttered. F stands for the final. Okay, so we have reached a conclusion, and this is the final basis. But the important thing is that if you look at the objective function, the opt will sit here as a scalar, and the non-basic variables will be here, and their coefficients will all be greater than or equal to 0. Yeah, so this is the final tableau. I don't know why I just called it tab. Okay, it got erased. Yeah. So is this clear? Does everybody remember that when simplex terminates with an optimum, this is where we are? Okay. It gives a proof of optimality. It tells us that nobody can do better because this form of the objective function was a consequence of our equations. And if you think about it, this form was actually derived by taking the original equation, yeah, where there was C transpose X, and to that we kept adding various multiples of those equations, which is reminiscent of what we did when we even formulated our dual linear program. So what simplex seems to have done is done some kind of operations which we consider legal when we wrote our dual linear program. But let us not think too much about that. Let us focus on the last row here. Let's focus on the last row. So at this point, what is true? Okay. We originally used to have here the objective function was of the form C transpose X. And we finally came down to writing this objective function like this. Why did the objective function, which used to just have variables here, turn out like this? As I said before, we took this objective function and we took these equations and we multiplied each of those equations by some scalar. At every step of the simplex, some variable or the other is being eliminated. But we know that when you want to eliminate some variable, it is the same thing as multiplying some row, some equation by some scalar and adding it so as to cancel out that variable. Some other variable will come in because of that. Okay. So what we did was we started with the original C transpose X, and then we took our equations, and this equation I'm writing it as B minus AX equals 0. Yeah, B minus AX equals 0 were our equations, and we multiplied them by some scalars, Y transpose, And now with foresight, I have chosen the same y. But we just know that simplex must have multiplied them by some scalars, and it obtained this form of the objective function. So this form of the objective function is obtained by simplex by starting from C transpose X and eliminating some variables. Is this okay? Yeah. If you see in maybe the last lecture, I had also given an explicit form for this coefficient, and that should make it even more precise as to how this what multipliers were used to obtain this equation. But right now we just know that some multipliers exist, some y's exist, so that this is true. Now just rearrange this equation. What do we get? We get C transpose X on the left. Yeah, this Y transpose B I have written here. Opt I have written here. This Y transpose AX I have moved to the right. And this is an equality. Yeah, equality of expressions which involve variables. Okay, this is an equality, which means that whatever these scalars were, the constant term on the left must be equal to opt. That means there must exist a y which corresponds to the actions taken by the simplex method, so that this opt was obtained by taking some linear combination of the b's. The b's contributed to opt. This is something we said before also. The scalars arise out of the scalars on the right-hand side of the original system of equations. And what can we say about C transpose X? Well, C transpose X is equal to this. Now, you see, this R, yeah, this R is a vector of constants, but each of those constants is greater than or equal to 0. That means on the right-hand side, if you look at the basic variables have the same coefficient as in this. That means for the basic variables, the coefficient of any basic variable on the left-hand side, which is Cj, yeah, some component of J, C, is the same as what Y transpose A gives. And for the non-basic variables, the coefficient on the left might have been Cj, and the coefficient on the right is Y transpose A's jth component minus Rj, where R is a positive quantity. That means for every non-basic variable, C transpose J is Y transpose A's jth component minus Rj. That means it is bounded by the jth component of Y transpose A. For the basic variables, it is equal. For the non-basic variables, Y transpose A is only doing better, meaning it is dominating it. But isn't that what we demanded? B transpose Y must be equal to opt, and for every other variable, A transpose Y must dominate the corresponding component of C. For basic variables, it's not just dominating, it is equality. And because of the R and the fact that simplex terminates with R, which is positive, yeah, but there is a minus in front of R, yeah. Because simplex terminates with R, which is positive, we can conclude that for all non-basic variables as well, the corresponding component here dominates this component. That is the proof of strong duality. That's it. Okay. You do the hard work in simplex. You assume that simplex terminates because you understood the lexicographic rule. And we know that in the end, simplex would come and rest in this very nice position. And think about this, and you conclude strong duality. Yeah. So I've said a lot, and maybe in a rushed way. Would somebody like to ask a question? So our goal was to show that the dual has a solution y, which satisfies the two things. That is, the objective function value should match, and we see that it is matching. And the constraints must hold, and we see that the constraints are holding. No.
So Jacob, may I say something? So for the non-basic variables, we also know at optimum their value has to be 0. So we get complementary slackness.
So, yeah. So everything we are getting. Yeah. So that's right. So those variables were. Sorry, we know that the non-basic variables are all 0, and
right.
Yeah. So
either the corresponding constraint is tight, or the variable is 0.
So I would have liked to say that I'm working with this equality system, so I'm a little worried about saying that. I mean, my constraints are all equality.
No, I meant this. The dual LP.
The dual LP. In the dual LP, I have. That's right. So if you look at the primal solution, yeah, that's right. Yeah, that's right. So sorry, say that again. So yeah.
So for any what is the subscript of X you were using for any
J?
For any J, either it's basic, in which case the corresponding constraint in the dual LP is tight because you have Cj equal to Y transpose Aj, or it's a non-basic variable, in which case its value is actually 0.
Good. Yeah, I know. So if you look at this, yeah. So we found what did I say? We found a dual variable y out of simplex. But so Kavita points out that let us try to see in what way this is satisfying this inequality. I mentioned that this equality actually holds with equality for some variables. And which are those variables? Those are those variables which form the basis. But wherever this holds with strict inequality, yeah, it must be the case that the corresponding corresponding xj's are actually 0 because they are non-basic here. Yeah. So if an optimum, yeah, some variable is so it has to be if in the dual some inequality is not tight, then the corresponding variable of the primal must have been 0. Yeah.
Exactly, that was a non-basic variable.
It must have been a non-basic variable. Well, yeah. All right. Okay, so yeah, please ask. I mean, it's actually once you do it yourself, you start imagining. I don't know. I'm very intimidated by symbols like this, but once you imagine that you have this system of equations all written down, and all you are doing is linear combinations of them, and you've got this solution. And if you were a little patient, I think this derivation from simplex method is quite straightforward. If you believe that this is what happens at the optimum, which involved a lot of work. We had to do lexicographic rule and all that.
I have one question. Sorry,
Please.
I have a question.
Yes.
So suppose the dual has only equalities, then can we reverse this and?
Yeah. So actually, the dual of the dual is the primal itself. If we do the we can turn everything around. Yeah. Okay. So, but I haven't told you how to take duals of. See, we started with an equational primal, and I told you the process for taking its dual. But here we have a dual where inequalities are appearing here, not equalities. So what I'm going to do very soon is give you a general recipe, any program, yeah, how to compute its dual. So then I hope it will answer your question. Yeah. Is that roughly what you're asking, or?
Yeah, no. So the simplex steps, can we revert them?
That's right. Instead of solving the primal, you could solve the dual. Yeah.
Yeah.
And the dual might come out to be unbounded, might come out to be infeasible, or it might come out with an optimum solution. If it comes out with an optimum solution by the simplex method, it will be the case that that optimum is also the optimum of the prime.
Okay.
Yeah, but maybe this answers another question, which was maybe asked very early. Finding a feasible solution is the same as solving an LP. Yeah, you see, we certainly find that the primal and the dual, they must have the same value. So if we can find a feasible solution of the primal and a feasible solution of the dual where they agree, then that must be the optimum solution. Okay. So what we can do is, instead of explicitly writing this minimize and maximize, we write all the equations with x and y both and equate their objective functions. So we create a system of equalities and inequalities where we collect together all the inequalities from the primal, all the inequalities from the dual, and also add one more equality which says that the dual's objective must be equal to the primal's objective. And if there is somebody who is very good at finding feasibility of a system of linear equations, we hand this over to them. And if they are able to find a feasible solution, then we know that feasible solution will be optimal simultaneously for both of them. Okay, so instead of the binary search method with a slightly bigger LP, feasibility leads to solving the original maximization and minimization problems with just one query to the feasibility oracle. So rules for dualization. Now, the principle is the same. We have the original linear program, which is a primal, which is a maximization program. And we would like to derive from the maximization program an upper bound for that maximization program by manipulating the remaining equations, all the inequalities we have. We don't necessarily have equalities and non-negativity constraints. There may be inequalities which are going either way. Yeah, we'll keep it very general. And there are variables which may be constrained, which are constrained to be positive, which are constrained to be negative, blah, blah, blah. Okay. So then, but the principle is the same. When you have an inequality and you would like to make use of it, you cannot multiply inequalities by negative numbers. Okay. So you have to, because we are keeping all the variables on the left, scalars on the right. So whenever you have inequalities, you must be careful about what sort of multipliers you use for them. Okay, that's all. So let us do that. So suppose we have a primal and you have variables x1 to xn. We will have a dual, which we should think of as multipliers for the rows of the various inequalities. Yeah, the rows of the prime. These are the multipliers. There are m of them. I'm sorry, what did I do? Should this be n? I think it's n.
Yeah.
Yeah, I hope it's n. Yeah. Okay. So because I'm going to write a times x. Yeah. Okay, good. So you never get anything right. Yeah. So the variables x1 to xn, here the variables are y1 to ym, but we'll come to this part later. Yeah. Let us just see. So we defined our matrix like this. The right-hand side will be a scalar with m components. The objective function will look like this, where the C will have scalars, but n of them, because it has to provide one scalar for each of the x's. Yeah. And now we have constraints. So the inequalities can be of three kinds. Yeah, there are these m rows. Some of them are written in this way, some of them are written in this way, some of them are written in this way. Well, those that are written in this way, you could have multiplied them by -1 and turned them into this way. But let us just keep it general here. Yeah. And the variables also, we will allow all kinds of constraints. Much of it is just vanity. I mean, I think in the end, you could reduce the cases, but somehow the translation between primal and dual becomes more. I mean, it's possible to do this in this generality, so let us do it. Okay. Yeah. So we have this maximization problem. Then, how is the dual constructed? Well, so this is a very mechanical thing that I'm telling you, but it just follows. So you are going to say that I'm going to use multipliers. So what care must you take with multipliers? If the inequality is already like this, then the corresponding yi's should be greater than or equal to 0. And if the equality is going the wrong way, whereas we are looking for an upper bound, on the objective function. So we need to reverse these inequalities. So we better choose yi's which are less than or equal to 0. If you have equalities, and this was the case that we discussed earlier, yeah. If we have equalities, then we have no constraints. Yi's can be any real number. Okay. Yeah. And we would like to find the best upper bound that we can. So we say that our dual LP is a minimization problem, yeah, which seeks to find the best upper bound. Okay. And now, what should be the relationship between A transpose? Yeah, sorry, it should have been like something like AY transpose. But since we come to the prime dual and we like all our variable vectors to be row vectors, we start putting transposes all over the place. But what do the inequalities look like? Well, for each column of the original primal, now there will be an inequality which relates the scalar in the objective function, the Ci, with the column of the primal. That is, after you multiply the scalars with that column, it has to dominate, either be greater than or less than or equal to. Okay. Now, if your variable is non-negative, yeah, then the sense, the left-hand side of the dual must, what am I saying? Made a mistake. Yeah. So the equations you have to write as greater than or equal to. That is what we did, if you remember, when our variable, the examples, the special case that we did a little earlier, all our xj's were greater than or equal to 0. That's why we said that A transpose Y must be greater than or equal to C. But now we are going to be slightly, more nuanced. For variables which are where this sort of non-negativity constraint holds, we will impose the condition that the left-hand side should be greater than or equal to this. If xj is less than 0, then the contribution to the objective function, yeah, should dominate, yeah, the contribution from this, yeah, Y transpose A or something like that. So the inequality goes in the other direction. If xj is unconstrained, then we better have equality, yeah. Otherwise, we cannot claim that what we are obtain on the right-hand side dominates the optimum of the left-hand side. So these are the rules, yeah, for constructing a dual from the primal. Now, if you see, the things are so symmetric, yeah, between x and y, I could just have sort of reflected it about this vertical line, yeah, and there is this business of minimum versus maximum, but the rules are the same. Okay, so if you have a maximization problem, you go this way and get its dual. If you have a minimization problem, you can imagine that you went this way, and you could have called this the dual of this program. Questions? Okay, so this is just a mechanical process of obtaining the dual from the primal. Now, what all can happen? Yeah. You see, if you look at the primal, it could be infeasible. or it could be feasible and bounded, or it could be feasible and unbounded. Yeah. Now, look at this case. Yeah. So if it is feasible and unbounded, that means now we know that if the dual had any solution at all, if the dual had any feasible solution, it would form an upper bound. It would provide an upper bound for the primal. But the fact that the primal doesn't have any upper bound implies that the dual doesn't have. So if it is feasible and unbounded, then the dual cannot be feasible. Yeah. So the only possibility is that the dual is infeasible. A similar argument applies here. Yeah. So for these two rows, these are the only possibilities. Now we are left. Okay, so again, if it is infeasible, similarly, this cannot be feasible. So yeah, I don't know what I'm saying, but some of these things are ruled out by weak duality itself. Okay, weak duality already says that, for example, could it be that the primal is bounded and the dual is, sorry, what did I say? Yeah, so we know that, yeah. So these entries, yeah. So if the primal is feasible and bounded, then it has an optimum solution. And if it has an optimum solution, strong duality tells us that simplex will give us a feasible solution for the dual, which is taking the same value. Okay. So if it is feasible and bounded, the only possibility is that the dual also is feasible and bounded. This we got from strong duality. So these things cannot happen. Okay. So similarly, if you do the primal, if you work from the dual, you will get that if it is feasible and bounded, the only thing that is possible is this. Okay. And the remaining cases, yeah. So if you pick up any feasible unbounded primal and write its dual, it will automatically turn out to be infeasible. So this case can happen. And similarly, if you take any infeasible primal, well, sorry, if you take some dual program which is feasible and unbounded, the corresponding primal will turn out to be infeasible. And I let you imagine there are situations when you can cook up an LP which is infeasible and its dual also is infeasible. Okay, so yeah. So this is where we are.
So you're saying supposing LP is infeasible,
Yes.
then it is not always the case that there exists a dual which shows that the LP is infeasible.
Yeah, so the dual program may be infeasible also. Yeah.
Okay.
Yeah. But in any case, what your primal is will be declared by the simplex method. Yeah, simplex method doesn't leave any ambiguity. If you run it and you're patient enough, it will come to rest, and there it will tell you, yeah, whether it was well, the auxiliary linear program itself will tell you whether it is infeasible or not. And after you have figured out that it is feasible, simplex will come and tell you whether you have a direction in which you can travel arbitrarily and yeah, satisfy be feasible and increase the objective function indefinitely. Or it will say that, look, here is the optimum and here is my witness for the fact that it is optimum because all coefficients have become negative. Questions? Now, we proved the duality theorem using the simplex, yeah, the strong duality, at least where all equations were less than or equal to, yeah. Oh, I didn't do that, did I? Yeah. So I proved it only for a special case where all equations were Yeah, so maybe I should do that. I forgot to make a slide for that. Did I do that? No. Okay. So maybe I'll just leave it at that. What I would like you to do is that suppose the primal was of the special kind, was of a different kind, not of our equational kind. It had constraints like this. So what would we do? If it had constraints like this, we would introduce slack variables and turn it into the old kind of LP. So there will be some special variables that you will add, m of them. Yeah. And now what I would like you to do is take the old duality with those yi's, the new variables xi's that you have added, and look at the duality, strong duality that we already proved, and see what you can conclude about the strong duality for this. In particular, how will you extract from that simplex method a solution to the new dual? This dual is of a slightly different kind. Yeah. So I'll let you think about that, or I'll make it an exercise. It's of course worked out in the book. Okay. So I'm sorry. Yeah. So my strong duality theorem, unfortunately, is restricted to equational form. But you can imagine that this form can be converted to the other by adding slack variables. And then you run the old duality theorem and do a little bit of manipulation with the variables that arise, and you will get the duality theorem for primals and duals which bear this relationship with each other. So typically, and I mean, somehow the geometric view of LPs, we have been somehow being very mechanical, equation-based algebraic view of LPs. I mean, which is rewarding in some way. You seem to be always very sure of what you're saying. Okay. But, we have eyes and we like to visualize. So to geometrically visualize things, there are other ways of thinking about LPs and polytopes and cones, yeah, and separation between one convex object and another, or one convex object and another point. Okay. So these separation theorems, are there in other areas of mathematics also. Okay. So there's a different approach to LPs. And typically, when restricted to the area of LPs, what one uses or proves is this lemma. I mean, there are actually many versions of this lemma called the Farkas lemma. Yeah, Farkas lemma. And there are various versions of it. So I would just like to tell you what the Farkas lemma is. We will soon prove one of them. Yeah, but we will not use the simplex. So these are all equivalent. We will see. Yeah. So whenever you have a lemma like this to prove, you can just plug it into the simplex method, and from the conclusion you can derive. Yeah. Yeah. So let us see. So if this is feasible, so suppose you have an equation of the form ax equal to b and x greater than or equal to 0. If it is feasible, then, sorry, the left, this is true if and only if this is true. Okay. Now, this direction is easy. Yeah. So if ax equals b, yeah, then it cannot happen that this is true. Yeah. Do you see that? So see,
That is weak duality.
Sorry?
This is basically weak duality. Right?
This is
ax equals to b. Ax equals to b is feasible implies y transpose a greater than equals to 0, and inner product y comma b is negative is infeasible. This is just weak duality, right?
This is just weak. Yeah. So you're already seeing duality in this. Yeah. So yeah. So, but this is weak duality, and it will be proved the same way. That is, you multiply both sides. Yeah. So if so if you multiply both sides of this equation by x or something, so yeah, when you compare with this, it will contradict this one. Yeah. So, but the other direction is the more interesting direction. Yeah. That is, if such a system is infeasible, yeah, then there is a witness to its infeasibility of this kind. Okay. So maybe should I do it more carefully? Why is it that if this holds, this cannot be infeasible? Okay, so let us, it follows from things that we have done, but let us see. Yeah, so suppose Y transpose AX is greater than or equal to 0. Yeah. Now, if you have a feasible solution here, you multiply the first equation by that. So what do we get? Let me try. Yeah, I'll mess it up, but let me try. Yeah. So Y transpose AX, yeah, will be equal to, I multiplied both sides, is equal to 0. But AX, AX is equal to B. So suppose the left-hand side was feasible, then AX equals B, and Y transpose B will be equal to 0. But this says Y transpose B is -1, and that contradicts this fact. Is this clear? Suppose the left-hand side was feasible, then there is a special X star, yeah, this X. Multiply this equation by that X. Yeah, sorry, Y transpose AX is greater than or equal to 0. But the left-hand side, because AX is equal to B, this Y transpose B is -1. So this and this, the left-hand side and the right-hand side both cannot hold. So if the left-hand side holds, the right-hand side must be infeasible. Okay. So I hope this was clear, but just play around. In most cases, one direction, I believe these directions will always be easy. They just follow from this. Yeah. So here, the difference is that in some cases you have equality here. Yeah. But you have non-negativity constraints. In some cases, you have inequalities here. In some cases, you have inequality, but X is unconstrained. And all of them will basically follow from weak duality. But what is traditionally done is that this lemma, one of these versions, this one, will be proved first. Yeah. And from that, the strong duality will be extracted. Okay. So this is called Farkas lemma. So what we will do is we'll prove one of them, and we will see which one. Yeah, maybe the first one. Yeah, and but by a different method. Yeah, and that's so the reason I'm doing that is because I want to introduce you to one more method, one more object that you will have heard of in other areas. Okay. So the general principle about inequalities is this. So if a system of inequalities is not solvable, I mean, it is infeasible, then it is possible to derive a contradiction from them. Now, derive a contradiction. What does? Yeah. So derive a contradiction in a special way. That is, just take these inequalities, multiply them by scalars, yeah, and non-negative scalars, and add them up, and you should get this contradiction. Whenever you have some inequalities which are not satisfiable, which are, the reason I'm saying satisfiable is because there's something else on my mind. Okay, so which are infeasible, then they are infeasible for a very basic reason. That is, this inequality can be derived from them by taking non-negative combinations of those inequalities. So this is the principle. And if you prove this principle, then we are done. Okay, because all of them, basically you can, any of these equations, you can write, this is a system of inequalities. You treat these also as inequalities. And if you are here, you can treat them as two inequalities if you want, less than equal to and greater than equal to. Yeah. So all these are questions about something being infeasible. Yeah. And the reason that this part is infeasible is because there was an X which satisfied some constraint. Okay. Yeah. So if something is infeasible, it is for a reason. Yeah. Because we can derive such an inequality from it. And why is this true? Yeah. So what I want to tell you is the Fourier-Motzkin elimination method, which is also another method to prove strong duality. Okay. It is very similar to Gaussian elimination that you have done in linear algebra. Sorry, maybe I should pause. Yeah, everybody is very quiet today, and I don't know if I'm making sense at all. Yeah. Kavita, you want to say something?
No, it's all very
fine. It's fine. Yeah. So let us see. Suppose instead of inequalities, we were given equalities. Okay, so I was hoping that it would be more interesting if I did this on the fly. So that is my problem. So suppose you are given some system of equations. You're given a system of equations. Let's go back to linear algebra. And we were asked, does this system have a solution? Now, what we are taught is that you put this system in row echelon form. Yeah. And if you ever get a row which has become zero here and non-zero here, then you can say that the system is not solvable. Otherwise, it is solvable. That means from these equations, by scaling them and adding them, one can derive the following contradiction. A system of equations is not solvable, yeah, does not have a solution, it's infeasible, of equations. If it is possible to derive 0 equals 1 from them by taking linear combinations, the coefficients involved in those multipliers involved can be positive or negative, which we kind of understand from our previous discussion is because we have equalities. The corresponding theorem is what we are trying to prove. Yeah, that is, if a system of inequalities now is not solvable, then a different sort of contradiction, not 0 equals 1. It's a contradiction that will involve the inequality sign. That means a smaller number, and for us it is 0, will have been shown. Sorry, a bigger number, 0, a bigger number, is less than a smaller number, that is minus 1. Okay, so such a basic absurdity will be derivable from this. Now you should compare this also with things in logic. Yeah. So when you have a system of clauses, and that's why I was talking about I was slipping into satisfiability language. If you have a set of clauses and if they are not satisfiable, then it is possible to derive from them a contradiction by the resolution method. Okay. Yeah. So resolution method says that if some two clauses are true, then some other clause must be true. Yeah. And the same, if some two equations are true, then their convex combination must also be true. So the same sort of logical pattern goes on. Yeah. And in the end, resolution says that if you can derive the empty clause is satisfiable from the original clauses, then the original clauses were not satisfiable. Yeah, they were infeasible. But there, the absurdity was the empty clause being satisfiable. Here, the absurdity is 0 equals 1. In the principle that I stated above, the absurdity is 0 is less than or equal to minus 1. Okay. So all these steps that we perform in these, adding one equation to the other, taking two clauses, and if there is a variable in common, eliminating it and putting the two clauses together, these are valid operations. They are sound. Yeah. So the word sound is used. But the kind of deeper theorem usually is that they are complete That is, whenever there is infeasibility, they will lead to a contradiction. In the case of row echelon form, this is a theorem in your linear algebra book, that if the system is infeasible, eventually you will get a 0 and a row where the right-hand side is non-zero. Okay. We are trying to just do the same sort of Gaussian elimination, and the word elimination here appears for the same reason. Okay. So why is this statement true? Yeah. So let us see. So again, we will try to find a solution to a system of equations. Okay. So let me just write down. Yeah. So finding a solution by variable elimination. It is like Gaussian elimination. We will eliminate one variable at a time. We will get a new system. We will try to solve it. Yeah.
So here x greater than equals to 0 or
sorry, say that again.
Here x greater than equals to 0 or
no. This is just an equation. If you had x greater than or equal to 0, you have to somehow include it. Include it in this. Yeah. We are just working with the fundamental problem of inequalities. Ax less than or equal to b. Yeah. And so here is a method for solving them. Yeah. We could have used simplex, but I'm going to suggest another method, and this method is due to Fourier, and it's called Fourier-Motzkin. So how does this work? Well, look at the first variable. Yeah. Consider all right. So here was this x1, and this x1 was appearing in many equations with various coefficients, 5, -7. Yeah. Now, each of these equations, each of these inequalities, yeah, says something about x1. For example, because this 5, the scalar 5 here is positive, this inequality, I could move everything to the right and divide by 5 and obtain an upper bound on x. Yeah, so this gives you an upper bound on x1. And this gives me, in this case, because this is a negative coefficient here, I can move 7x2 to this side, move the b2 on this side, and then divide by 7, and I get x2 on the right hand side. Yeah, so this gives me a lower bound on x1, and so on. So each of these inequalities,
a lower bound on x2, right? For the second.
Sorry, I don't know why I wrote x2. I'm focusing on the first variable. I don't know why. Yeah, I should have written x1. Everywhere I'm focusing only on x1 and trying to ask what is the opinion of that inequality about x1. Some inequalities say I have a lower bound in terms of other variables. Some other inequalities say I have an upper bound in terms of other variables. Just like in Gaussian elimination, each equation had an opinion about x1. X1 should be this linear this combination of the others. Okay. And then if you think about it, when we eliminated, when we did row echelon form, we said, well, if x1 takes a certain value, its value is determined by the others. Let me substitute that into all the other equations. And once you substitute it into all the other equations, x1 is eliminated. Okay. So you are taking the opinion that the first equation has about x1, and you are pushing it into the other equations. Let us do the same thing. Some equations have upper bounds on x1. So this whole business from x1's rather self-centered way of thinking is everybody is out to get x1. Okay, x1 is here. Some people have there are some upper bounds, and some equations have formed lower bounds. Is this much clear? Any system of equations, we could take x1 and either write down all the upper bounds for it in terms of other variables on this side, and all the lower bounds for it in terms of other variables on this side. Yeah. Now, I just take every one of these equations, every one of these expressions, and ignore x1 and just put a less than equal to. That is, I take the Cartesian product. So if there were maybe m over 2 equations on this side and m over 2 equations on this side, I take all these inequalities and form a new system of inequalities. But this system doesn't have x1 anymore. These are just inequalities among the remaining thing. And do you see that? If this new system is feasible, then the original system is also feasible.
Yes.
Yes. Yes. Take the feasible values, then each of the quantities that these evaluate to must be less than or equal to each of these quantities that these guys evaluate, because that is what you compared each of them with each of them, and that blew up. Yeah. In resolution, some of you, when you have clauses, when you try to eliminate x1, yeah, you take each clause which has x1 in the positive form, x1 in the negative form, and eliminate x1 in the positive form, x1 in the negative form. There are parallels between what you do in resolution, what you do in Gaussian elimination, and this. I will not belabor this point too much now. Okay, I'm saying it once. So once again, if after eliminating x1, this new system, which consisted of all this Cartesian product, when I say Cartesian product, every left-hand side, you play it against every right-hand side and ask for feasibility. Then if you draw the number line, all these quantities on the left will evaluate to various values under that feasible solution, and the greatest of them will be less than or equal to the smallest of the values that these guys evaluate to. Yeah, sorry, this is my number line somehow. Yeah. And there will be a space for x1 here. Okay. Is this clear? Same as Gaussian elimination. After you have eliminated x1, if you have found the solution for the remaining system of equations, take that solution and substitute in the first equation to extract the value for x1. Okay. Similar thing we are doing. Now, go to x2. You have a system of equations. All these m squared over 4 inequalities, some of them have x2. So, some of them might have had x2 on both sides. You, of course, combine them, collect the coefficients. Each of them becomes an honest inequality. There might be scalars on both sides. You write them nicely. x2, some of them provide upper bounds for x2, and some of them provide lower bounds for x2. And you keep doing this. You eliminate x2 now. Again, take a Cartesian product. The number of equations might blow up.
But on the number of equations be exponential.
Yeah, we are just trying to prove the principle. Okay, we are not trying to say that this is an efficient method. Yeah, but what happens if the original system was infeasible? When will you get stuck? When after you have eliminated, when you are looking at the last variable, yeah, xm. The lower bounds and upper bounds will look like what? What will appear on the left? What will appear on the right? There will be many, many equations. Each of them,
functions of x1, linear functions of x1 to xm minus 1.
No, we have eliminated x1 to xm minus 1.
So, there will be just single numbers in the last
single numbers. Yeah.
Yes.
And when is this infeasible? It must be that this is infeasible. If we started with an infeasible system and we applied this procedure, yeah, we must come to such a situation sometime for some variable, let's say, yeah, where there are scalars on the left, scalar on the right, and we have got this inequality to satisfy. And it must be that this number is
greater than the right hand number.
Greater than the other number.
Upper bound is greater than the upper bound.
Yeah, the lower bound is greater than the upper bound. Now you move the lower bound to the upper bound, you get 0 is less than or equal to maybe minus 27. Yeah. And then you can scale this by a positive constant and you are getting 0 less than minus 1. Okay. So now I let you convince yourself that the inequalities that we are getting at each step, the Cartesian product is actually obtained by taking the corresponding inequalities here. One of them had x1 and with a positive sign, the lower bound had x1 as a negative sign, the upper bound had an x1 in a positive sign. So it is feasible for you to multiply the first equation by some scalar and add it to the second equation so that x1 gets eliminated. And the resulting equation will be precisely the equation involving this. So every equation that we obtain in our life while doing the Fourier-Motzkin elimination method is actually a non-negative linear combination of previous equations. And if you believe my story, by taking non-negative combination of the previous equations, you must be able to derive this. So this is a kind of non-algorithmic, non-computer science way, but it has a certain charm to it. You don't have to mess around. You don't have to look carefully at coefficients. You don't have to keep track of tabulas. Yeah, you just say that, yeah, I will just do what Gauss taught us. Eliminate variables at a time. And if it is infeasible, I must come to a situation in the end where the lower bound is greater than the upper bound. I move the lower bound to the right-hand side and I must get a contradiction. Okay, so I have not said everything absolutely precisely. Yeah, the proof in the book does this by induction. For each variable, you do induction, just like we understand row echelon form. But if you want to do it formally, you'll probably have to write an inductive proof for why the row echelon form theorem is true. Okay, but I hope it was intuitively clear. If it was not intuitively clear, or you see a pitfall or some fallacy, please ask. Yeah, I would like to. I really like this. Yeah. And
if there are only lower bounds or upper bounds, then you just eliminate the variable.
Yeah, then you don't need to bother about the variable. Yeah. Sorry, if so, some equations may not involve x1 at all. I should have said that. Those equations that inequalities don't involve x1 at all, you keep them. If for x1, the only thing that appears are upper bounds, then you forget about those, because if only thing you are telling me is upper bounds, after having solved the other equations, I will find the smallest upper bound. I will set x1 to something less than that. That means basically x1 has a very happy situation if their bounds are from only one side.
Sure, that's all. Thanks.
Yeah, but if there are, it's not as if there are only upper bounds available for x1, we can stop. There might have been inequalities which talked only about the other variables. Those we keep with us. Yeah, I should have. So that those sort of imprecision was there in mind. Yeah, yeah. Thank you. Yeah, yeah, yeah. Any other questions? So I want to just maybe just summarize. There is a lot in this chapter in the book, but we have done Farkas lemma, and if you use this principle of Fourier-Motzkin, you will be able to prove one of the versions of Farkas lemma. And we did strong duality through the simplex method. I did not explain every part of it, but again, the essential ideas we have covered. Okay, so let me just summarize. So yeah, what did we do? So to solve an LP, we have this initial polytope, and we have this objective function, but we sort of expand the polytope by adding some fake variables and solve the auxiliary LP. Okay, and yeah, so somehow this reminded me of the title of a Hindi movie. So we are trying to solve this problem, and this is our objective, but we are actually solving some other linear program. So let's see if I can get this done. Okay. Yeah. So yeah, we wanted to solve this, but we get something else. So maybe what I'll do, yeah, so I'm sorry, I'm just being a little facetious. I'm actually going to play a song, yeah, and then I'll keep quiet and I will just go through these slides. Okay, so let me play the song. Let me know if you can hear it. Actually, can you hear this?
Yes.
Bye.
Why is this TFR?
Yeah. It's sort of a tribute anyway. Yeah. Bye.
Thank you.
Thanks, Akmal.
And what is DL?
Yeah, let people guess. Yeah. Okay. Bye. Meet next time.